Welcome back to the deep dive. Today we are getting on to some seriously high-tech vessels. We're talking about liquefied natural gas carriers, LNG carriers. These things aren't just, big ships. They're essentially giant, super regulated thermos bottles designed to haul huge amounts of natural gas, chilled way down to what, minus 163 Celsius? Brutal.
Oh, brutal is definitely the word. And the stakes involved, they're immense. I mean, think about it. The stuff expands like 600 times if it vaporizes upon release. So if you overfill one of these massive tanks, you're risking, well, everything. Structural damage from sloshing liquids, huge environmental impact. Preventing that overfill, it's absolutely fundamental, non-negotiable for safety.
Right. So our mission today really is to dig into the architecture, the redundancy, and maybe the failure points of the high-level alarm systems, the systems designed specifically to stop those disasters. We're peeling back the layers of engineering safety that hopefully keep LNG moving safely around the world.
And we're looking at the real rule books here. Stuff like the IMO IGC code for gas carriers, SOLAS, and industry best practices from groups like OCIMF and Suchitoto. These aren't just suggestions. They mandate very specific layers of protection.
Okay, let's unpack this.
Right. And the best place to start is probably defining those layers. The IGC code, Chapter 13 specifically, it requires two totally separate levels of high-level monitoring, the HL and the HHL.
Okay, HL and HHL. Let's make sure we get what each one does. The first one, the high level or HL alarm. When does that one kick in?
So the HL, that usually activates around, say, 95% tank capacity. You should think of it like an operational warning. The yellow light, maybe.
Yeah.
It's telling the cargo officer, okay, things are going fine, but heads up, you need to start managing the filling rate now. Slow it down because we're getting close.
Okay, 95%, slow down. So what if that HL alarm is missed? Or maybe the filling just can't be stopped fast enough for some reason. That's where the HHL comes in, the high level.
Exactly. The HHL, that's your critical final safety net, the emergency stop button, basically. It activates higher up, usually around 98% capacity. And what's really key here and fascinating from an engineering standpoint is how the rules demand this HHL system be totally independent. It cannot share components with the main tank gauging system or the HL alarm. It has to be a completely separate safety chain. Really crucial to avoid single points of failure.
Wait, hold on. When you say independent, what does that really mean in terms of hardware? You can't just program a different number into the same computer.
No, absolutely not. That's exactly what you can't do. Functional independence is, well, it's paramount. It means separate everything. The HHL needs its own sensor, its own power supply, often drawing from an emergency source, its own signal wires, its own processing logic, completely distinct. If the main ship power fails or the main cargo computer has a glitch, the HA must still be sitting there watching the tank level, ready to act.
Got it. Like having two totally different phones, different networks, different batteries, just in case one fails completely. Okay, so 98% HHL goes off. What happens then? Immediately.
Immediate automatic action is required. Besides the obvious loud alarms and flashing lights on the bridge and in the cargo control room, the IGC code mandates it ties into automatic shutdown functions. This system has to have the authority, the capability to instantly trigger the stop of cargo pumps, the closing of manifold valves. It forces a stop to the cargo coming aboard.
And you mentioned power resilience. SOLAS has a role there, right? Making sure this thing stays powered.
Absolutely. The SOLAS Convention, Safety of Life at Sea, mandates that critical alarm circuits like the HHL are connected to the ship's emergency power supply. So even if the main generators go dark, this ultimate overfill protection stays alive.
Okay, so we've got the rules demanding this separate powered automatic shutdown system, but how do engineers actually build these things to be that reliable under pressure? That takes us into safety instrumented systems, doesn't it?
Yes, exactly. LNG overfill prevention, it's formally classified as a safety instrumented function, a SIF, and it's designed within a broader safety instrumented system or SIS framework. These are designed following really strict international standards like IEC 61508 or 61511.
And what do those standards actually enforce? What's the goal?
They formalize the whole process of risk reduction. For something like LNG overfill, the system is typically engineered to meet a safety integrity level 2 target, SIL2. That SIL rating, it corresponds to a specific calculated level of reliability, basically a very low probability that the system will fail when you actually need it to work. It quantifies the safety performance.
SI2. Okay. And hitting that kind of target, you can't just put one sensor in and hope for the best, right?
Yeah.
Which brings us to voting logic. This sounds interesting. The system argues with itself.
Yeah, it's a pretty clever way engineers handle a tricky balance. You want to avoid two things: failing to detect a real danger and tripping the alarm unnecessarily, what we call spurious trips.
Right, false alarms must be a huge pain.
They are extremely disruptive and costly. So think about the options. You could have a 1-out-of-1 system. One sensor sees high level, alarm goes off, maximum safety against overfill. Yes, but highly susceptible to false trips if that one sensor glitches.
Okay, makes sense. So what about needing two sensors to agree? Like 2 out of 2 or 202?
That cuts down your false trips drastically. Great for operations, but it introduces a really dangerous failure mode. If one of those two sensors fails silently, like it just stops working but doesn't signal a fault, then your entire safety function is dead. You need both to agree, and one isn't voting.
Okay. So that's a hidden failure waiting to happen. Not good.
Definitely not good. Which is why for critical systems like HHL, you very often see 2 out of 3 logic, so 3 independent sensors. The logic only requires 2 of those 3 sensors to agree that the level is high before it triggers the alarm in the shutdown.
I see. That sounds like the sweet spot. If one sensor fails, maybe it reads low or just goes offline, the other 2 can still agree and trigger the alarm if the level is truly high. And if one sensor glitches and reads high erroneously, the other 2 reading normal will prevent a false trip.
Exactly. It tolerates a single component failure, whether it's the sensor itself, its wiring, maybe even its specific power feed without causing a spurious shutdown. And it maintains the safety integrity because you still need 2 working sensors to confirm the dangerous condition. It's robust.
But hang on, putting in 3 sensors, 3 sets of wiring, all that. Doesn't that triple the maintenance? Is that complexity worth it?
That's a very fair point, but yes, the analysis, the SIL calculations, they consistently show it is absolutely worth it. The cost of maintaining those extra components is tiny compared to the potential cost, financial and human, of an LNG overfill incident. That investment in redundancy is basically the price of entry for achieving that required SIL2 risk reduction.
And underlying all this voting logic is the idea of fail-safe design, right? You want the system to shout if it breaks, not just fail silently.
Precisely. Fail-safe is fundamental. If the system detects an internal fault, say, the wiring to a sensor gets cut, or it shorts out, or the power flickers, it must default to a safe state. Usually that means activating a dedicated fault alarm to tell the operators, hey, something is wrong with the safety system itself. This often relies on continuous line monitoring, checking the electrical health of the circuits.
Okay, so we've got this smart, redundant, fail-safe system, but what's it actually up against inside that tank? The environment sounds like the real monster here.
Oh, absolutely. This is where the textbook design meets the harsh reality of cryogenics. You're trying to get an accurate level reading inside a tank full of liquid sloshing around at minus 163 Celsius. You've got challenges like the low dielectric constant of LNG itself, which affects certain electronic measurements, plus constant boil-off gas creating vapor and the ever-present risk of ice forming.
Let's walk through some of the sensor types then, because it sounds like they each have their own battles with this cold. What about simple mechanical float switches? Seems basic enough.
Simple can be good, especially for testing them later, but floats are really vulnerable in LNG. The biggest enemy is icing, or frost bridging. Imagine ice building up around the float mechanism, physically jamming it. It could get stuck in the down position and just never signal a high level, even if the liquid is rising right past it. A dangerous, undetected failure.
And I guess the ship moving around doesn't help either.
Not at all. Sloshing is a huge problem for floats. The liquid surface is constantly moving, which can make the float bounce up and down rapidly. We call it chatter. This causes nuisance alarms, which is bad because operators might start ignoring them, getting desensitized. So floats usually need protective tubes, stilling wells, and sometimes even heaters to combat ice.
Okay, moving up the tech ladder, what about non-contact radar? Like free space FMCW radar. Sounds perfect. No moving parts, doesn't touch the liquid.
It avoids the direct contact issues, yes. But it faces its own physics problems. Frost or condensation building up on the radar's antenna lens can basically blind it. And heavy boil-off gas, like a thick fog inside the tank, can scatter or absorb the radar signal, making it difficult to get a clean reflection from the liquid surface.
Right, like trying to use radar in a blizzard. And guided wave radar, GWR. That uses a probe, right?
It does. A GWR sends the signal down a physical rod or cable, which gives it high accuracy because the signal path is controlled. But that probe is right there in the cryogenic liquid. So it's very susceptible to ice building up directly on the probe, which can mess up the measurement or even block the signal entirely. Again, often needs a stilling well.
And we should quickly mention capacitance sensors.
Right. Capacitance probes, they're compact, no moving parts, but they can also be affected by vapor condensate icing on the probe surface. And their reading can sometimes shift a bit if the exact composition and thus the dielectric constant of the LNG cargo changes.
Okay, so it seems like everything struggles with ice or vapor. And you mentioned a caution about ultrasonic sensors too.
Yeah, the source material generally advises against using ultrasonic point sensors for these critical high level alarms in LNG. The issue is the chaotic environment inside the tank. You get vapor cushions, pockets of gas, and significant temperature differences within the liquid and vapor space. These all tend to scatter or distort sound waves, making ultrasonic detection unreliable for a critical alarm threshold.
So if every single technology has its own specific weakness, ice, vapor, sloshing, condensation, then the best approach has to be mixing them up, right? Using different types for the redundant sensors.
Exactly that. Technology diversity is best practice for redundancy. If you're building that 2 out of 3 HHL system, you wouldn't install 3 identical GWR sensors. You might use, say, 1 float switch, 1 free space radar, and maybe 1 capacitance sensor. The idea is to minimize the chance that a single environmental condition, like a specific type of icing, could disable all 3 independent safety layers at the same time. That's real system robustness.
Right, makes total sense. Okay, moving toward the end here. How does that HHL alarm signal actually connect into the ship's overall safety actions?
It plugs directly into the ship's emergency shutdown system, the ESD. Usually there's an ESD1 for local actions and an ESD2 that might involve the ship's shore link. So the HHL signal hits ESD1, which immediately trips the relevant cargo pumps and closes specific manifold valves on the ship itself. ESD2 often extends that shutdown command across the loading arms to the shore terminal, telling them to stop pumping from their side too. It's a coordinated stop.
And for the crew watching all this, the displays, the human-machine interface, or HMI, must need to be incredibly clear, right? What makes a good alarm display?
Absolute clarity is vital. Seconds matter. The HHL alarm has to show up clearly in the main control spots, the bridge and the cargo control room, or CCR. It needs to be both audible, so you hear it, and highly visual, typically a bright flashing red light. And crucially, the alarm indication must be latched.
Latch. What does that mean exactly? Why is latching important?
Latching means that even if the condition clears temporarily, maybe the ship rolls heavily, and the liquid level momentarily dips below the 98% mark, the visual alarm light stays on, solid, until an operator physically acknowledges and resets it. It prevents the alarm from just blinking off if the level fluctuates. It ensures the operator knows that the HHL threshold was breached, even if just for a moment. It's a record that the safety system activated.
Okay. We've touched on icing and sloshing as things that can cause failures. Are there other, maybe more hidden threats related to just keeping these systems working long term?
Definitely. Besides the obvious sensor issues, a couple of big lurking problems are often related to installation and aging. One is something called cable wicking. With the constant extreme temperature cycle, super cold LNG, warmer ambient air moisture can actually get into the cable ends and travel, or wick, up inside the insulation. This degrades the insulation over time, potentially causing signal loss or false readings. You need really high quality cable glands in installation. Another hidden threat is more human related. Operator desensitization from those sloshing chatter alarms we talked about. If the system generates too many nuisance alarms because it's not tuned right,
People might start ignoring them, or worse, try to bypass them.
exactly, which leads to the need for things like debounce logic in the software, basically a small time delay filter.
But that sounds like a tricky balance itself. You need the delay to ignore the quick splashes, but not so long that the tank actually overflows before the shutdown kicks in.
Precisely. That debounce time has to be carefully calculated and tested, short enough to meet the safety requirements, but long enough to prevent constant false alarms from normal sloshing. It's a fine line.
Which I guess brings us to a really critical maintenance task, proof testing. This sounds like more than just flicking a switch.
Oh, it's much more. Proof testing is absolutely vital for maintaining that SIL2 safety rating. It's done periodically, maybe every 6 or 12 months, sometimes longer depending on the SIL calculation. Its specific purpose is to find those dangerous undetected failures. The kind of failure where the system looks okay on the surface, the light might be green, but it wouldn't actually work if a real demand occurred. Automatic self-tests can't catch everything.
So what does doing a proof test actually involve then?
It means you have to test the entire safety loop from end to end. You physically stimulate the sensor, maybe by carefully raising a float or using a test magnet or injecting a simulated signal right at the sensor input. Then you have to verify that signal travels correctly through the wiring, triggers the logic solver as expected, activates the correct alarms in the CCR and bridge, and confirms that the final output commands to shut down pumps and valves are actually generated. It's a full functional check. So if we kind of connect all this back, you really start to appreciate the complexity. Moving LNG safely depends on this incredibly deep layered defense. You've got the 95% operational warning, then the totally independent 98% HHL system triggering automatic shutdown. And making that reliable involves regulatory mandates, sophisticated voting logic like 203, careful sensor selection, and ongoing battles against, well, physics at minus 163 degrees.
Yeah, the technical side, the robustness built in, it's genuinely impressive. Designed to handle failures, diagnose itself. But the source materials always seem to circle back to the human element being the final, crucial layer. These sophisticated systems can be bypassed for maintenance, but it has to be under strict controls, like a formal permit to work system. Anomalies need prompt reporting.
Which really leads to a pretty profound thought, doesn't it? We engineer incredible technical reliability, independence, redundancy, fail-safe logic. But what happens if that near-perfect system is compromised? Not by a broken wire or a faulty sensor, but by, say, operator confusion under pressure, or a delayed response, or someone improperly bypassing a system thinking they know better. It raises this big question. In a world striving for automated safety, how does that continuous, focused human training and procedural discipline remain perhaps the most vulnerable, yet ultimately the most essential element for keeping the whole system truly safe?
That's a fantastic point to end on. Knowing the tech is one thing, but trusting the procedures and the people, that's maybe the hardest part. Okay, that's all the time we have for this.